let's start. So today's class is somewhat different from the 3 previous classes that we had, because today I'm going to speak about something really very complicated. Of course, we'll try to find some simple aspects in it, but the complexity is a lot higher than what we saw before. And yeah, we'll see how we manage with it. I must admit, I also have difficulties with the material, so we'll see what comes out. So let me recall that today we are looking at an example of a finite dimensional quantum system. It's called a spin chain, and we already seen the basic elements of it. So first of all, now the Hilbert space is finite dimensional, but this dimension can be pretty high. So the dimension of H is 2 to the power n, where n is the number of sides of the chain. Perhaps I'll recall a little bit how one works with those tensor products. So you were already working with tensor products at the exercises, but let's recall a little bit how it works. So first of all, let's fix the basis in C2. Let's choose just the standard basis. So sometimes, well, we'll be using the notation E1, E2 for those two vectors, or sometimes the physics style notation, maybe like plus and minus, or in words, sometimes one says spin up, spin down. Whatever it is, it stands for the same basis. Now, we can form a basis in H, and the basis in H can be built, for instance, in the following form. So you choose for each of the sides one of those two vectors, and you take a tensor product of them. So this set is a basis in H. In particular, we'll be interested, or we'll be using a lot, the following vector. So this is just a product of E1s. Or you can choose E2, any of them. But so, or in the physics notation, this will be plus, 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 plus. So we'll see that it's kind of nice to use this vector from time to time. Now, what's the question? We should equip now this space with a Hamiltonian, and the Hamiltonian we defined in the following way. I already don't quite remember which sign we chose, maybe the minus sign, and here will be sum from 1 to n, and here sum over A, sigma AI, sigma A, I plus 1. So these are sigma matrices acting on the side I, and these are sigma matrices acting on the side I plus 1. And the notation here that sigma A n plus 1, right? Because when I is equal to n, here appears sigma A n plus 1, which does not exist, is by definition the sigma matrix for the first side. So you think of this notation now periodically. Right, so that's a concrete operator. It has some physics motivation, but for us, it's just an operator which is defined in a somewhat complicated fashion on this finite dimensional vector space. And one standard question that we have in quantum theory or in linear algebra is to find eigenvalues. That is the spectrum. And eigenvectors of H. So today I'll show you some kind of answers to those questions. And the answers are in some way interesting, but probably the method in which they obtained is even more interesting. This is some kind of extraordinary method which led to huge developments both on the physics and on the math side. And in particular, this question led to discovery of what is now called quantum groups, which is a big part of algebra and representations theory. So this is like kind of somewhat strangely looking, but not particularly generally looking question, right? It's a concrete, after all, to be honest, it's a concrete matrix on a vector space of a huge dimension, right? Linear, from a point of view of linear algebra, that's it. Maybe let's spend 1 minute on discussing this Hamiltonian. So let's consider just one term. So these are sigma matrices acting on two neighboring sides. And of course, this is now an operator acting on this whole space H. But let's think for a second about it as an element of endomorphisms of C2 tensor C2. Now I think at the exercises you were already looking at the form of this particular operator. Now this is a four-dimensional space, right? So we can actually write it as a matrix. So and if I'm not mistaken, if we write it in the following basis, so that's exactly the basis that I outlined here. Right now there would be only two terms, I and I plus 1 in this four-dimensional Hilbert space. So this is a tensor product of two copies of C2, and this is E1 tensor E1, this is E1 tensor E2, and so on. Right? If I'm not mistaken, what we get is something like this. And all the other entries are 0. Is it correct? So by now I think you've written it many times at the exercises. All right. So let me now do the following. Let me add to it a unit matrix. So just a unit operator. So then you see what will happen. So those minus ones get cancelled, those ones get doubled, and I can write it as twice 1, 0, 1, 1, 0, 1. So what does this element do to elements of C2 tensor C2? It does something very intuitive. So what does it do? Where does it send E1 tensor E2? To E2 tensor E1. Right, it permutes the two copies. So this is called the permutation matrix or permutation element. So what we see now is the following, that the sum over A, sigma AI, sigma A, I plus 1, plus the unit matrix is twice the permutation I plus 1. Or we can now rewrite the Hamiltonian in the following form, minus j, sum over I from 1 to n, and here twice the permutation I plus 1 minus 1. So this is in some way, for some purposes, is easier because now all of a sudden you have a very intuitive way to see how this operator acts. In particular, from this fact, it follows that omega is an eigenvector of H. Indeed, omega has all the elements the same, right? So the permutation matrix acts simply by 1, or actually all the permutations, they act by 1. Since if you permute E1 and E1, you get E1 times E1, right? So, so H acting on omega is equal to minus J, and here the sum from 1 to n. But here we have simply 2 minus 1 times omega. So, and this is equal to minus nj times omega. Maybe I should say that I'm not sure, like, kind of, I chose relatively randomly this coefficient. In various both physics and math sources, people choose this coefficient differently. In particular, sometimes they shift it such that the eigenvalue on omega be 0. So you see, I got an eigenvalue minus nj, but some people prefer it to be 0. Then they just shift it by a constant. So in the literature, you may see the different normalizations of this H. Also, sometimes they divide by various factors, by 1/2 or by 1/4 or whatever. But it doesn't matter so much for us. Okay, so maybe the last thing I want to introduce a small piece of notation. Let me introduce the combinations of the Pauli matrices sigma 1 plus or minus I sigma 2, and these are simply upper and lower triangular matrices, and if I'm not mistaken, the value will be equal to 2. Okay. So up to now, nothing happened, right? I just restated the problem and discussed a little bit the normalizations and the structure of the Hamiltonian. Now, something important will happen. We're going to introduce the notion of L operators. And so L operators, there will be one for each lattice side. So they will depend on some parameter z, let's say complex number. And interestingly or crucially, they are not operators acting on H. So they are operators acting on H tensor with one more copy of C2, which is called an auxiliary space. So we already have, recall in H, we already have n copies of C2. But now we add one more. Now, Li will be given by an explicit formula. And I will write it in the following way. I will write it as a 2 by 2 matrix. So that's the 2 by 2 matrix acting on this C2. So the entries will be operators acting on H. So let me try to do it. So here it will be Z times the unit matrix plus I over 2 sigma 3I. So here it will be I over 2 sigma minus I over 2 sigma plus I, Z over I minus I over 2 sigma 3I. Right. So this will be, that's a strange concrete matrix with entries being operators acting on H. Maybe one more formula for it. So the same thing is Z times the unit matrix in this auxiliary space C2 tensor 1 in H plus I over 2 sum over A sigma A C2 sigma AI. So you see it looks a little bit like a Hamiltonian again, shifted by some strange extra 1 which carries a parameter, but this thing is a Hamiltonian, the same formula as those terms that we saw before, but now it's mixed between one of these spaces which in the decomposition of H and this auxiliary space. A posteriori, a huge theory was developed or is developed around this construction. At the moment, it looks like an ad hoc construction, but if our course were a course in algebra and more exactly in representation theory of quantum groups, then we would have obtained this expression as an outcome of some general machinery. However, at the moment, we just see it as it is. All right, after all, that's a definition, right? Well, certainly we have a right to do it in this way. So let me introduce one more notion. It goes under the name of a quantum R matrix, but actually this is just a 4x4 matrix which depends on a complex parameter. So a concrete 4x4 matrix, let me write it down. So there I had, right, so and as usual, all the other elements are equal to 0. So it has this something on the diagonal and this non-trivial 2x2 block in the middle, similar to the matrices that we have there. Okay. Now let me state a theorem. So this theorem is a kind of computational fact. We'll see part of its proof just to better understand what it is about. So sometimes it also goes under the name of RLL equal to LLR as a shorthand. And it says the following. Let me write it down and then explain notation. Right. So the first question is, what are these funny 1, 2s, right? And where does this identity take values? So actually what happens in this identity, we introduce 2 copies of the auxiliary space. So this means that this is an identity in operators which act on this gadget C2 tensor C2 tensor H. Now, how does it work? In particular, this R12, right? This is a 4x4 matrix. So this 4x4 matrix acts here, and to act on H, it simply acts by 1. So this is equal to R tensor 1. So let me call this space 1 and this space 2. Now let me write Li2 of W. So this guy acts by 1 in the first space, and in the product of the second and H, it acts by Li of W, right? So by this formula. Now you see, I decided to write Li2 and Li1 I didn't want to write. Now why? So that's because this Li1 has 1 in the middle, right? So I don't quite know how to write it nicely. So it's the same construction, but it acts by 1 on this guy in the middle, and it acts as Li on the product of those 2 spaces. So invent a good way to write it. Okay, so it's a huge identity, right? In operators on this space, and the claim is that those Li's satisfy this identity. Of course. So we're not going to prove it in full detail. However, I will give you some part of proof that just because at the moment it looks very abstract. We need to work with it more concretely. So that's why. So here perhaps we'll need one more piece of notation. So let me denote the matrix entries of the operator Li, those operators acting on H. Let me introduce a notation. So let me denote those matrix entries A, B, C, D. Let me recall, they are all endomorphisms of H. Maybe one more small remark. Notice that, so here I write B of Z and C of Z, right? These are those matrix entries. So they're actually constant. They don't depend on Z at all. And these guys, they are linear functions of Z, right? So the proof consists of 2 steps. Step 1. Let me simply write down this identity as a matrix identity. Here I'm a little bit unsure how much of a blackboard it's going to take, but let's hope it fits here. So if I write too big letters, tell me, because that's dangerous. So right, okay. Okay, so this will be this R, right? I copy R. So this is Z minus W plus I. This is Z minus W, I, Z minus W, Z minus W plus I. And all the other things are 0. Now, what is this next guy? Let me try to write it down. So you see, we have now 2 auxiliary spaces. And this one will be acting in the first auxiliary space. In the second auxiliary space, it acts by 1. So let me write it down, and then you tell me whether you agree. You see those small blocks, they correspond to the second space, and the big blocks, they correspond to the first space. So you see how it goes. You take this A and you multiply by 1. So, and that's this A times the unit operator in the second space. So that's how it looks like in practice. Now, what about the second one? The second one acts in the second space. So, and it's multiplied by the unit matrix in the first space. So that's why it looks like this. Of course, now it gets easier, right? Now the equation says right? So it's not complicated. Well, of course, it looks somewhat horrible and messy, but it's not complicated. So it's a product of 3 4x4 matrices. Oh, yes. Okay. So it's not difficult, but right. Is it better? Okay. Right. So so this matrix equation is equivalent to 16 relations between those operators A, B, C, and D. So we're not going to write down all of them or derive all of them, but we can easily imagine that, well, there are those 16 relations. Let me still derive maybe 2, and I will write without proof the third one, because I'll need it later. So, so let's do the following. In the result, let's say I will be only interested in the top row, because otherwise it gets too complicated. So let me write the top row of the left-hand side and of the right-hand side. Oh, let me try at least. So Maybe you can help me. So first I will be multiplying those two matrices. Okay. So on the top row I will see A of Z, A of W, right? Then what? So then I'll have A of Z, B of W, right? A of Z, B of W. So what's the next one? B of Z, yeah, right. B of Z, A of W. And then the last one is B of Z, B of W, right? Right, so this is the top row. And then you see, fortunately here this matrix is so easy, it will be simply all multiplied by Z minus W plus I, right? So it's all multiplied by now what about this one? So so first we need the top row. We need the top row here. So it will be A of W, right? A of W, A of Z, then what? B of W, A of Z, then what? A of W, B of Z, and then B of W, B of Z, but now that's not the end of the story. That's just the top row of this product. Now we should multiply it by this, right? But maybe one small remark even before we go further. So you see here, I write those symbols in some order. And that's the order how they come up here. I cannot exchange the order because those A of Z, so A of W, so all these things, they actually operate as acting on H. So and I think I tried to take care and write it exactly in the order as it is on the other blackboard. So okay, now let's go further and let's multiply by this matrix. So I'll try now to write the answer. So this guy is simply multiplied by Z minus W plus I, right? So now the next entry, or here it becomes more complicated or more interesting. It becomes Z minus W times B of W, A of Z, plus I, A of W, B of Z, right? So the next entry becomes what? Now I, A of W, B of Z, plus Z minus W, B of W, A of Z. And the last one is Z minus W plus I, B of W, B of Z. So in fact now I should erase this one, right? And that's the third term is not correct. Oh, yeah. So this is B of W, A of Z, and this is A of W, B of Z. Thanks. Actually, that's the third term that I was interested in, so I better get it correct. I must admit it was a kind of horror story in preparations. So I think I get it correctly once in 3 times, so kind of. All right, so these two expressions are equal to each other. So in particular, look at this last entry. So the last entry, for instance, is telling you that B of z, B of w is equal to B of w, B of z, right? Now, I'll be interested in the third term. So, so this equation I will. So B of z, A of w is I, B of w, A of z, plus, here, z minus w plus I, as z minus w, A of w, B of z. I would like to rewrite it in the following way. A of w, B of z is z minus w plus I over z minus w. B of z, A of w minus I over z minus w, B of w, A of z. So this is some kind of, you see, this is a simple-minded relation which just says that those operators commute. So this relation is a complicated, interestingly looking, funnily looking relation. So all in all, there will be 16 of them.
B actually doesn't depend on the parameter, right?
Okay, maybe I should say one thing about our strategy. Remember, this is step 1, right? And in step 1, I suggest, let's forget about the concrete form of the operators. Yes, you're right, but you're also wrong. So you're right, but let's forget about it for a moment. So we simply say, okay, so this statement, this matrix identity, it's 16 relations between A, B, C, and D's. Let's see what they are. In fact, this will prove to be useful. So maybe just one more, because we'll need it later today. D of w, B of z is w minus z plus I over w minus z, B of z, D of w minus I, w minus z, D of w, B of w, D of z. I think I do remember all those equations now by heart, but just in case, yeah, I think that's correct. So, and there are many more, right? There will be many more relations. In particular, one of those relations I would like to derive and give you an independent proof. So, right, one can crunch those matrices, multiply them, and derive identities, but there is one identity which is particularly important, and it has a particularly nice proof. So let's introduce a new notation for A of z plus D of z. So this is actually the trace of the matrix A Li of z. Now let's take this relation and let's rewrite it in the following way. So I write it like this: Li1 of z, Li2 of w is equal to R12 inverse Li2 of w, Li1 of Z R12. Of course, right, that's the same relation. I just took an inverse. Took this R matrix on the other side. Now let's take a trace on the first and second space. So remember, we have here this huge product, C2 times C2 tensor H, right? So that's where this operator acts. Now let's apply to it trace in C2 tensor C2. So the resulting identity will be an identity for operators in H. Now what happens when you take a trace of that guy? You obtain trace Li of Z, right? Now when you apply it to this guy, you get a trace of Li of W. Now you take a trace in this four-dimensional space, and notice that the R matrix, it only lives there, right? It doesn't do anything to H. So this means that you can use this cyclic property of the trace. And this means that under the trace, these two factors, they will simply disappear, right? So that's what we get. So this is a kind of probably that's this consideration which in the beginning justified those huge and incomprehensible formulas. So in other words, we have this identity. So those traces, they commute. And obviously, you can also crunch those relations, those 16 formulas, and you will get the same. So these are, I think these are those formulas that we'll need later today. So as I said, so this was step 1. Now what is step 2? We're not going to spend much time on step 2. Step 2 is very easy, or so verify those 16 relations for those A, B, C, D. Now, examples. Let me recall that, say, for instance, B of Z is I over 2 sigma minus, right? So actually, it does not depend on Z. Now, we need to verify the relations. So one of those relations is B of Z commutes with B of W. Well, now it's obvious, right? It's actually the same operator. And to be honest, when you multiply two of them, remember it was a kind of nilpotent lower triangular matrix. So actually both sides are 0 anyway. So nothing depends on Z and W, and both sides are 0. Of course, it might be somewhat more interesting to verify those. So let's still see maybe this one. So what is T of Z? So this is Z times 1 plus I over 2 sigma 3 plus 0 times I minus I over 2 sigma 3. So this is simply 2Z times the unit matrix. Now, T of W is of course equal to T of W, T of Z, because the unit matrix commutes with itself and with everything else, and so on. So, right. So let me finish this hour by saying that we introduced a very complicated, somewhat nice, because maybe of this calculation, but hugely complicated formalism. After all, for checking something which is very elementary to start with, right? So at the moment, it absolutely doesn't. So this is a nice theorem. This is a beautiful observation. But at the moment, it absolutely doesn't look justified, right? So we're using a huge machinery for computing or expressing simple facts about 2x2 matrices. Now, after the break, I will show you the next theorem. And I hope this next theorem will fully justify the exercise. OK, well, let's have a break. All right, so let's continue. Now I would like to show you some extraordinary construction. It starts in a very simple way. So we introduce yet another operator which goes under the name of a transfer matrix. So it again depends on the parameter z. And it is simply a product of all the L's. So again, that's an operator. Acting on the auxiliary space. I decided to multiply them in this order. One can choose an opposite order if one wants. So on the notation, from time to time or in the proof of some statement, I will be also adding the index n, or I will be sometimes dropping that index. So it says that that's a product of n of them. And similar to the notation we used before, it will be convenient to write it as a 2x2 matrix with entries being operators on H. And I'll denote them by capital letters A, B, C, and D. So now those A, B, C, and D are endomorphisms of H, and they are polynomials in one variable. Note that these small ABCDs were constant or linear functions. Now, when we take a matrix product of n of them, in general, they become degree n polynomials. Now, a proposition which says that M of z, so this complicated product, it actually verifies the same relation as the elementary L operators we saw before. So that's probably another discovery which motivated the popularity of this whole machinery. Again, that's the proof is very easy. But it's an extraordinary fact. So we want to We want to compute this quantity. And the proof will be by induction. So the base of induction we already proved. If n is equal to 1, then L1 satisfies RLL equal to LLR. So now let's make the induction step. Well, let me rewrite it in the following way, right? Mn is actually a product of Ln times Mn minus 1, right? Just by definition of Mn. So the product of all the rest, that's Mn minus 1. And here we have of W now recall that this identity, it takes values in the endomorphisms of C2 tensor C2. So that's auxiliary. Tensor H, and H is also a product of many, many C2s. Now, I would like to argue that actually these two operators commute. So why is that? That's because this guy, M1, it acts on this space and on all these spaces, but not, on all these spaces, but not on the last one, right? Because I didn't use Ln in defining Mn minus 1. So that's where M1 and minus 1 acts. Now L2n, it acts on this space, that's the second auxiliary space, and on the last copy of C2 inside H. So that's where L2n acts. So they simply act on different spaces in the tensor product, and they're equal to 1 on the other one. So that's why they don't talk to each other, they commute. So this is equal to R12 Ln1 of Z, Ln2 of W, and then M1 of Z, Mn minus 1, 2 of W. But now we can use this RRL equal to LLR for L. And this gives us Ln1 of Z, of W, Ln2 of W, Ln1 of Z, R12, M1, N1, M1 and minus 1 of Z, M2, and minus 1 of W. But now see the magic of the story. Now this expression, RMM, that's exactly the left-hand side of RRL. And now by induction hypothesis, M verifies RRL. So we can do it again. So that's so this gives us now Ln2 W, Ln1 of Z, M n minus 1, 2 of W, M n minus 1, 1 of Z, R12. Now by the argument which is similar to the one I gave before. So this guy and that guy, they don't talk to each other. And I can exchange them. So, and then in the end, I will get back my L2n times m2n minus 1 of w, which is mn2 of w. And then I will also get back m1n of z. So you see somehow that's a kind of nested calculation. So you can make each step and then the induction works. So things that you want to commute, they commute. Somehow there is a little bit of a magic in it. And as I say, maybe I should stress again. So today, many things that we saw, they look like magic. In principle, they have some scientific explanation, which would take another course to explain. Right. Okay, so we have this. Well, why is it interesting? So this is interesting for the following reason. So this proposition implies. Remember when we were looking at the proof of the theorem on the previous hour, we said let's forget at the moment what is the concrete nature of small a, b, c, d. We just derived those 16 relations, or maybe whatever. We wrote down part of them, but we actually know how to get all of them, right? Now you see, M is a lot more complicated object. So their matrix entries are again operators, but now they are polynomials of potentially huge degree. But we didn't think what was the nature of A, B, C, D in the proof. So this means that capital A, B, C, D, they verify exactly the same relations as small a, b, c, ds. In particular, those relations here, you can exchange small letters by capital letters, and you get, I will not be rewriting those relations, we'll then later so we'll keep them and later use for capital A, B, C, D, but let me just rewrite two of them. So for instance, we get the commutativity of capital B's. And we can again define capital T as a trace of M. Trace in C2 in the auxiliary space. And we get now we actually know that T of z is a polynomial in z of the degree which is bounded by n, right? So it's a product of n linear functions. So the most what we got is n, and here we have some So here is the fact. So T0, Tk, together with the operator L3. So remember, there were those operators L, also acting on H. Is a quantum integrable system. So actually part of the homework is to show that L3 actually commutes with those T's. So that's probably one of the, or at least in the beginning, this was one of the major uses of this machinery. So it allows you to create lots of operators which commute with each other. So you see, kind of, you start with simple building blocks. Then by multiplying them, you construct operators which are polynomials of huge degree, arbitrarily big, whatever you want. And then each coefficient, right? Each coefficient is a commuting observable, commuting with all the others. Maybe I would like to add one small remark. So let me recall that Li of z is equal to z times 1 plus I, and here some array sigma a c2 sigma ai. Now we actually know that this operator, we can rewrite it as a linear combination of identity and, sorry, I, was it I over 2? Could you check? Yeah. Yeah, and I know, you'll see why. I now noticed it. So we can rewrite this operator as a linear combination of the permutation between auxiliary space and I minus the identity. So let me rewrite it one more time as z minus I over 2 times identity plus I times the permutation. So it follows that there is one somewhat special value of z, which is equal to I over 2. And at that point, so this operator is up to multiplication by I equal to the permutation matrix. It's interesting to compute what is this transfer matrix? How does it look like at that point? So this is ln of I over 2 ln minus 1 of I over 2 and so on, L1 of I over 2. And, well, this is equal to I to the power n. P, let me call this thing A for auxiliary. So it is PA n, PA n minus 1, and so on, PA 1. So let's see how it acts on a typical vector. Let's say we have a vector which is equal to V in the auxiliary space times V1 in the first one, and so on, times the Vn in the n space. So what's going to happen? So I first apply, maybe I will act vertically. So I'll first exchange A and 1, right? So it will be V1, V, V2, and so on up to Vn. So then at the next step, I should exchange V2 and A, but at the place of A is now this V1. So the next step will be V2, V, V1, and so on, Vn. So if we continue, in the end we will obtain Vn times the V times the Vn minus 1. And of course, we always had whatever. We always had I to the power n. So that's the first vector, and that's the end result. So the end result is a cyclic permutation of the vectors, including Va, and times I to the power n. Now, here is an exercise. So remember, maybe we are even more interested in the operator T than in the operator M. So after all, T is the operator which acts on our Hilbert space, and not on this Hilbert space times the auxiliary space. So let's consider T at that special point, I over 2. That's now an endomorphism of H. Now, what's your guess? So you have a cyclic permutation, and you take a trace of it over the first space. What are you going to get? What's your feeling, right? It's a kind of linear algebra question. So the result is simple and surprising. Actually, the trace of a cyclic permutation is again a cyclic permutation. Right? On H, you can also permute. And if you take a trace over the auxiliary space, it will turn out to be a cyclic permutation again. Well, yeah, there is here some small thing to prove. So probably the last theorem that I want to formulate today is probably the most sophisticated and most interesting of all. Yeah, it goes under the name of Bethe ansatz. So you will see. So the word ansatz stands for some sophisticated formulas that we guess. So ansatz is a guess. So better guessed in some way an answer to a very complicated problem. And now we'll see not the original Bethes formulation, but some interpretation of Bethes results in applications to our problem. So consider a finite set of distinct complex numbers L of them, where L can be arbitrary. Such that they verify the following equations. Here it's relatively easy to So these are algebraic equations for those complex numbers.
Is here any imaginary unit or not?
This I and those i's are imaginary, yeah. Yeah, maybe you're right, maybe it's... Sorry for confusing notation. Yeah, those i's are square roots of -1. So then the vector, so we're now using them as arguments of the operators B and act on the vector omega that we were discussing in the beginning of our today's class. So let me better call it T of W. So then this is a common eigenvector of T of W for all W, right? They all commute, so it makes sense to ask about their common eigenvectors. With eigenvalue, which now depends on W and also depends on the solution of the Bethe equations, given by the following I hope I'm right. No, sorry. Well, so this is an answer of eigenvectors and eigenvalues of this integrable system. As you see, it is somewhat sophisticated, right? So these are solutions of some complicated equation, and the eigenvalue is rather complicated. So I'll spend the last 15 minutes by showing you a small part of a proof. In fact, so another small part of proof will be one of the exercises. And, well, so let's see. First of all, let's start with a case where L is equal to 0, right? So there are no z's. We're just looking at this vector omega. So remember, omega is this guy. Now we would like to act on it by the operator T of z, and this is trace This is a trace of a huge product. Now, a small remark. The operator sigma plus, right? So this is this operator. Acting on the vector E1, it gives you 0. Right? So this actually means the following. Remember, when you write a formula for Li of z, so you have something, 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 but here you have I over 2 times this sigma plus I. So now, a priori, this trace consists of many, many terms. But whatever you do, you're not allowed to use any of those lower triangular entries of L. Because once you have one of them, it will act on one of those E1s, and it will give you 0. Right? So for this calculation, you can actually think that Li is an upper triangular matrix. Well, but this simplifies the matters considerably, right? So let me write it in the following, maybe not completely correct way. So mod sigma plus, so I'm not allowed to use sigma plus anywhere. So mod sigma plus, this thing is equal to, well, now that's a trace of a product of upper triangular matrices. So I should simply multiply their diagonal entries, right? So this is a product over whatever, let's say k from 1 to n, and here z times 1 plus I over 2 sigma 3 I plus product of lower diagonal entries, which is equal to this. Now, sigma 3i, or sigma 3, has E1 as an eigenvector of eigenvalue 1, right? Because this guy is simply 1, 0, 0, minus 1. So this means that those sigma 3s I can actually replace by 1. So T of z acting on omega is equal to the following. It's a product. Oh, sorry, here would be k. So in fact, will be z plus I over 2 to the power n plus z minus I over 2 to the power n omega. And actually, this is the action of A of z, and that's the action of the operator d of z. So when L is equal to 0, there are no products, right? Because there is nothing where we should take a product over, and then the formula matches, right? So that's kind of okay. So we'll finish by proving the L equal to 1 case. So for that, let me consider a vector A equal to B of z times omega. And I would like to check when this is a common eigenvector of T of W's for all W's. So we want to compute T of W B of z omega, and this is A of W plus D of W B of z omega. Is it okay if I erase the first part of the proof? I prefer to keep the statement. Now, well, that's why I kept those horrible equations, right? Now, so I'm computing A of W alpha, which is A of W B of z omega. I'm sorry, my W and my omega, they're somewhat the same in writing, but they stand in different positions. So there is, so we should not confuse them. Okay. Well, we are now using this relation, right? We are now using this relation, and this gives z minus W plus I over z minus W B of z A of W omega minus I over z minus W B of W A of z omega. So why is it good to use this relation? That's because we already computed, just in the previous point, we already computed how A acts on omega. Right? Omega is a particularly simple vector, so we actually know that this gives us W plus I over 2 to the power n, z minus W plus I over z minus W, B of z omega, minus z plus I over 2 to the n, I over z minus W, B of W omega. Now, you see, at the moment it doesn't look very good, to be honest. Because we are acting by our operator on the vector, we do get our vector back with some horrible coefficient. So that's good. But now we also get some other vector. It doesn't look so good. So let me try to write a similar formula for D. So I probably won't be making a calculation Instead, let me simply, or can I? Do I have it? No, let me still do can we write the answer? Probably. At least we can try. So I'm trying to copy the other formula. So I should be getting w minus I over 2 to the n. Now w minus z plus I over w minus z. And now b of z omega. So one term will be again good. Minus z minus I over 2 to the power n. I over w minus z b of w omega. Right. But of course, fortunately, we are interested in the action of a plus d, right? So we are interested in this action. So first of all, note that so these two terms, unless I made a mistake, these two terms, they combine, so that we'll now see. So these two terms combine in the correct eigenvalue. I think I just need to change the sign in the numerator and denominator in the first fraction here to obtain this expression, right? And otherwise they match for the case of k equal to 1. But then we're getting one more term. Let me write it like this. Right? So I changed this. So here there were different signs, z minus w, w minus z. So I changed the sign up there. So I get this term, and this term has to vanish, right? So there is no hope to get an eigenvector if this term doesn't vanish. So if this thing vanishes, then is an eigenvector, alpha is an eigenvector with an eigenvalue given by this huge expression. And that was part of what the Bethe-Ansatz theorem was saying for L equal 1. Now, homework is to prove it for L equal to 2. And in principle, a similar argument would show that it actually works for any L. So let me finish. With a small remark. You know, I started all this story by telling you that we should diagonalize the Hamiltonian H and determine its eigenvalues. And now I was talking to you for 2 hours about something else. What about the Hamiltonian H? So it turns out that H can be expressed as a function of commuting quantities T0, Tn. And the eigenvalues, which will now be functions of Z1, Zk, right? So these are solutions of the beta equations. So the eigenvalue corresponding to the beta vector. And here I must say, again, like with normalizations, I'm not entirely sure. So there is always this minus j times n, which does not depend on k. And then the k-dependent part is as follows. So it turns out to be a rather simple formula. So it's a very simple function of zk's. L is a number, oh sorry, yeah, there were L of them, right? So, but these are solutions of the beta equations. So a priori, it's a simple function of solutions of a very complicated system of equations. Maybe, okay, so that's about successes. So maybe I should still tell you that I told you a very beautiful story, a very nice story, but at the moment, as I presented it, as a very incomplete story. In the following sense, one should still answer the following question. For which solutions of beta equations the corresponding vectors are non-zero? Because, right, I mean, if you got an eigenvector with a very nice eigenvalue and this vector is actually 0, so then it doesn't give you much information. So in principle, I think probably for this model the complete answer is known. But in general, in this beta and that story, this fact of the completeness, where you get a complete basis, or what kind of vectors you need for the complete basis, I think that's still, at least maybe some years ago, I still attended some lectures on new developments in this field. So this is still a field which is developing, and maybe one reason is that, as you saw, those beta equations, they are enormously sophisticated. They're just horrible equations, right? So you cannot just easily say something about their solutions. In particular, maybe one small thing, there are real solutions, but there are actually complex valued solutions which also contribute in this spectrum. So in general, this story, kind of, I showed you a relatively simple part of the machinery, but then there is a next stage in representation theory and in algebraic geometry where people study beta equations and this beta ansatz problem. Now, so this was, remember, our course. It comes in sections, and that was the section about finite dimensional Hilbert spaces. And I think for now we reached our summit in this field. So starting from next time, we'll turn to infinite dimensional Hilbert spaces and see what happens there. Okay, that's it for today.